We're going to go through today's notes in a couple of short videos. I will be looking to see that you've completed your notes next class, and I will be able to tell that you've completed the Schoology folders. So keep that in mind for today. Remember from our last unit that regular polygons are both equilateral. So when we say equilateral, that means all of the sides are congruent. And regular polygons are also equiangular, meaning that all of the angles are congruent. So that's going to be something important to remember when we are finding the area of regular polygons today. There's two vocab words that we often associate with polygons, and one is radius. So we know in a circle that the radius is the distance from the center to the edge. So the radius of a polygon is the distance from the center of the polygon to any vertex on the polygon. So in this picture over here to the right, if I draw from this center point to any vertex of the polygon, and remember these points are the vertices, so that's a vertex as well, this is a radius. So I would like you to label that in your notes. Sometimes we call this the circumradius because it's the radius of the circle that circumscribes the polygon. The other word that is probably new to you is the word apothem. So the apothem is the distance from the center of a polygon to the midpoint of one of its sides. So if this is the side, let's say this is the midpoint. So if I draw the center, the line from the center to the midpoint, that is the apothem, and it makes a right angle. So if I draw in other radii, so we said that's the apothem, that's the radius, we can really decompose this shape into triangles using the radii, and then the apothem is the height of each of the triangles. All of these triangles are going to be isosceles because the radius is the same going around the shape. So these are all isosceles triangles. All right, so we're going to come back to that in just a moment. We're going to use a lot of trigonometry today, which might be kind of exciting. We know the area of a triangle is base times height divided by 2, and we need to remember sine, cosine, and tangent. So when we take the sine, it's of an angle. It's a opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. And so TOA is our acronym for remembering that. All right, example 1. Find the area of the regular hexagon, so I know I've got 6 sides here, with a side length of 10 centimeters, show all work. So here's what we're gonna do. The first thing I would do is in my hexagon, I would go ahead and draw in all of the radii. And you don't have to use a straight edge, but I'd do it as neatly as possible. All right, so when we draw in all of the radii, we should have 1, 2, 3, 4, 5, 6 isosceles triangles. So when we draw in the radii, we get 6 isosceles triangles. I'm just going to write that down so I don't forget. We also know that the length of each side is 10 centimeters. So for all of these side lengths, they're all the same because it's a regular shape, so it's equilateral. So what I'm going to do is I'm going to just pop out one of these triangles, and we're going to just look at one of these isosceles triangles we made. And so we know that like these two sides are the same length, and we know that the length of this is 10 centimeters because we're told that in the problem. So if we consider the apothem of the shape from the center down, straight down to that midpoint, It's always perpendicular to the side. That is the apothem. So in this picture, that would be the apothem. And both of the sides of the triangle are the radii. Okay, so again, like I just popped out one of these triangles to look at over here. So in order for us to use trig to find the length of the apothem, which is what we need to find the area of this triangle, what we actually need first is to know what the angle is, and we're really going to consider one of these right triangles. So the reason in this first example I kept this circumscribed by this circle is that from like going around the center, there's 360 degrees right there because this is a circle. So we know that there's 360 degrees. So what we want to do is divide that by the number of triangles we made. So we made 6 triangles. I'm going to do 360 degrees divided by 6. And when we do that, that's going to give us 60 degrees. So what that means is that in each of these isosceles triangles we made, that top angle is 60 degrees. All right, so the next thing that we need to do is cut the triangle in half. So we're now just looking at half of that triangle. Oops, I drew it a little too big. So half of 60 degrees is 30 degrees. This is the apothem, and the original side length from here to here is 10. So this side length is now 5, because we're just considering the right triangle made when we drop the apothem in. Okay, so we could set up a trigonometric function to find the length of the apothem. So looking at the angle we know, which is the 30-degree angle, looking at that angle, we need to figure out what trig function to use first. So I know like this is my hypotenuse. If my angle's up here, this is my opposite side, and the apothem is the adjacent side. So it works out that we're calling it A for apothem because it's also going to be adjacent. All right, so we need to set up a trig function. We know the opposite. We're looking for the adjacent, so that means we have to use tangent since it's opposite over adjacent. So I'm going to just kind of write the work over here because I'm running out of room. So the tangent of 30 degrees is opposite, so 5, over adjacent A. So remember, when our number is on top, we can't multiply both sides by 5. But what we can do is, if I kind of think of this as a proportion, remember we could swap anything out diagonally. So I'm going to swap the variable and the trig function, and I get that A equals 5 divided by the tangent of 30 degrees. So I need my calculator. And in my calculator, I need to go to mode to make sure that I am in degrees. And then I'm just going to type in 5 divided by tan 30. All right, so I get about 8.660. That is the length of the apothem. And it's going to be in centimeters since this side's in centimeters. So the apothem in the triangle is about 8.660 centimeters. Okay, so now what we're going to do is we're going to find the area of one of those isosceles triangles. So we remember we have 6. I'm going to sketch one over here again. So going back to the isosceles, not the right triangle within it, we said all of the sides are 10 centimeters because that leg right there is the hexagon side. And when we found the apothem, what we really found is like the height of this triangle. So if we just plug this into our area formula, we know area is base times height divided by 2. So in your calculator, if we keep that number right there, we can now multiply by our base and then divide that by 2. So base times height, divide by 2. We should get about 43.301. All right, so that's the area of one of those isosceles triangles. And that's going to be in centimeters squared. Oops, sorry. And then the last thing is to just multiply that by the number of triangles. So since there were 6 isosceles triangles in the hexagon, I'm going to do 6 times 43.301. The most precise way to do that is to leave that number in your calculator, hit times 6. So the approximate area of our hexagon is 259.808 if we round centimeters squared. All right, there's going to be 2 more videos. I want you to do example 2 with the video again. When you get to example 3, I want you to try it before you watch the video.